I'm going to give you some of the answers you were struggling with. So some of you who haven't studied this are going to say, oh yeah, it's a good thing I haven't started. But no, you're wrong, you're the loser. Because if you don't struggle with it, you don't remember it, you don't retain it, you don't understand it. A lot of you dealt with this issue of stochastic gradient descent versus batch gradient descent. I didn't mention it in class almost at all, but it is mentioned in Tom Mitchell's book and in any other book about neural networks. The idea is that gradient descent is always about taking the derivative of the error, which is a function of the weights, with regard to a particular weight, and then multiplying it by step size, a small step size, and the negative of that is the change in the weight. This is the definition of gradient descent. Now, the global error can be decomposed as a sum of the error of each individual training example. So it would be TD minus OD squared, although this is for mean squared error, and it equally applies to any other kind of error. Number of training examples, make that n. And since this is a summation, you can shove the derivative inside, so this becomes negative eta sum of the gradient of the derivative of this specific TD minus OD squared. So the idea behind stochastic gradient descent is that you don't take a step in this, take a step in each one of these individually, one after the other. You reduce the gradient as if your entire training data was just a single training example. You reduce the gradient of that by one step, and then you go to the next data item, and you reduce the gradient of that, and then the next data item. As a result, and you cycle through all your data. When you cycle through all of your data once, that's called one epoch. Okay? This corresponds more or less to one step in the standard gradient descent, where you truly calculate the gradient based on all the training examples. Now, there's some subtle differences between, maybe not so subtle differences between the outcome in both cases. Which one is easier to understand mathematically? I think this one is easier, because there is a well-defined function that doesn't change. The function doesn't change, and you're always following the gradient of that function. And you're going to get to the minimum, to some minimum of that function if your step size is small enough. Stochastic gradient descent is a little harder to analyze mathematically, because you're not reducing the gradient of a single function. So you're alternating which functions you're following down. You keep following down the gradient of different functions with regard to different training examples. As a result, the different training examples could compete with each other. One of them pushes you in one direction, the other one pushes you in the other direction. So it could happen that at the end of an epoch, you end up exactly where you started. Furthermore, I suppose it could happen here too. That would mean you're in the minimum. But in a stochastic gradient descent does not mean you're at the minimum. Furthermore, you're not evaluating all the training examples from the same starting point. You have some starting point, you evaluate the first training example, take a step along its gradient, now you're at a different point, you're evaluating the gradient of the second example. So it's a bit of a mess. It's not easy to prove much about it, but on the other hand, it's practically sometimes much faster than the batch gradient descent. So this would be batch mode or batch gradient descent, and working on this, based on this, would be stochastic gradient descent. The reason stochastic gradient descent can often converge much faster is because it's a little bit like decision trees that have a lot of training data. The root node doesn't need to look at all the training data. Right? When you train a decision tree, the first thing you are you're asking is what attribute to put at the root. If you have a ton of data, you don't need all of it. Any subset of it, just like we saw in the exam, any subset of it is likely to result in the same root node. There's more information than necessary. There's an abundance of information. When you start training a decision tree, suppose you didn't do it completely stochastic gradient, but suppose you divided your training data into 10 batches, just like in the case of a tree. Then you can do the first step, or even the first few steps, based on just one of those batches. It would push you in the same direction, more or less, as if you had based it on all the data. So in the beginning, you start from a point that's so far from a good point that any amount of data would push you in the right direction. Even a single data point might push you in the right direction. And suddenly, as you do the stochastic part of one data point after the other, they all kind of point roughly in the same direction. There's some canceling going on, but they're mostly correlated. As you get closer to the minimum, now the different training examples start pulling in different directions. They each have their own minimum, so they start canceling each other more. So one take-home message from that is that you might want to start with stochastic gradient descent, and then at some point switch to batch. Or alternatively, you can start by training on a small amount of your training data and then gradually increase the amount, if you're trying to balance efficiency and time. Yeah, go ahead.
The data set that you've been given is so small that you actually do standards all the time.
Right, I agree, yeah.
In that case,
I wouldn't. The question is, the data set that we have is so small, you could do the whole thing. Why bother? I wouldn't bother with stochastic. I would go with batch. But you could if you wanted. One other advantage of the batch is that you're guaranteed that the error should keep going down on the training data, right? With stochastic, you're not guaranteed that, and I know some of you ran into problems, and in the longer term, over many epochs, it should go down. The nice thing about the guarantee that it goes down is that you can test your code this way. So even if you want to do stochastic, you may want to start with batch just to convince yourself that things are going down in batch mode, that error rate does go down from step to step. And when I say guaranteed, with a small enough step size, right? Is that what you want to say? Yeah. Yeah, the step size is always an issue. Yeah? I'll go to somebody else. Never mind.
In actual practice, how do you determine the step size? The learning rate.
You mean this, the learning rate?
Yeah, that.
0.01. It's a very good question.
Because there were like three numbers. There was like 0.1, and then in the left there was like also 0.05. Like
Right.
that's a lot of them.
So there are many, because this is a heuristic, there have been many super heuristics along the way to try to speed it up. For example, you can change the step size, the learning rate, during the process. One way to consider doing that is look at the correlation between two successive corrections. Every correction points in some direction in high dimensional space, right? It's the gradient. And look at the angle between the successive gradients. And if it's almost zero, you can afford to take a bigger step. If it changes, you should slow down the steps. There are other variations, by the way. There are methods that look at not just the first derivative of the error, but also the second derivative of the error. It's called the conjugate methods. There are lots of variations trying to speed things up. You can add momentum. Momentum is basically a way of effectively increasing your step size, but smearing it over many, many different corrections. Yeah.
So, a lot of hidden nodes. Does it correspond to us overfitting it?
That's the next topic I was going to talk about, a number of hidden nodes. So let's do that. Let me make sure that I covered everything I wanted about the stochastic gradient descent. So we talked about the difference between iteration and epoch. This is just terminology. An epoch corresponds to going over all the training data once. In batch gradient descent, epoch and iteration are the same thing. In stochastic gradient descent, you iterate over the training examples. When you iterate over all of them once, that's an epoch. All right, so let's talk about topology. So we're restricting ourselves to the case as a single output, and there's a whole bunch of hidden units, and here are the inputs. In Mitchell's book, for example, he talks about this kind of network as being a two-layered network because it has two layers of neurons. He doesn't count that these are not neurons, these are inputs. I like to think about it as a single hidden layer, okay? But this is why I insist on adding the word hidden so that it makes it less confusing, just terminology. So this is a single hidden layer, but you can also call it a two-layer network. If you restrict yourself to a topology with a single hidden layer, and we're going to talk a lot later about what happens when you add more layers, but even if you restrict yourself to a single hidden layer, how many neurons should you have here? What might happen if you have too few?
Your misclassification rate or your error rate is high.
Your error rate is high. You will not be able to bring your training set error rate as low as you want it to be. What does having too few units here do to the expressive power of the network? It reduces it. It increases the hard bias. There's a hard bias here. Not every function is expressible with, not every function of, say, 10 inputs and a single output is expressible in an architecture that have 5 hidden units. If I take out 2, even fewer are expressible. So the hard bias is going to be stronger, the expressive power is going to be lower. If the expressive power is too low, that means the correct function, or even a reasonable approximation of it, is not in that set, then you will not find it. That will manifest itself as not being able to reduce the training set error. What if you have way too many? What will happen then? I'm sorry? Overfit. Because the expressive power is going to be so large that the target function or approximations to it are going to be there in abundance. And it'll be relatively easy to find them. So when you have a large expressive power, you fit the training data, but you typically don't fit it through finding the regularities in it. Actually, what I said before is true, but is somewhat misleading. If you have a lot of neurons and a lot of expressive power, you would get a very easily very low error in the training set, not just because the correct function is in there, but because it's easy to find functions that happen to match your training data. So if you find the true target function in there, that's great. It will do well on the test data. But the problem is that when your expressive power is way too large, there are many more functions that happen to fit the training data, not because they latch onto the regularities that are really in the problem, but because they basically do a lookup, a table lookup of the training data. So networks have kind of a memory capacity of sort. They can memorize, to an extent, training examples. I say memorize, it's kind of hand-waving, but the idea is that if you gave them training examples that are random, completely random, so take some training data and randomize the labels and ask a network to learn it. With enough units, it will learn it. You may ask, what is enough units? And there's some rule of thumb that people follow to what is, how many units are needed to memorize how many training examples. But the remarkable thing is that they can memorize. And in fact, decision trees will do the same thing. If you give a decision tree randomly labeled data and you allow it to grow as much as it needs, it'll memorize it. So too few, the training data cannot be brought down to a reasonable level of error. Too many, you can easily bring down the training data error to low level. But what other symptom do you have? The test set error or the development set error is going to be high, because you didn't really learn the underlying regularity that we're after. You memorized the data. So what you want to do is you want to find the number of hidden units that give you enough expressive power to contain the target function, but not enough to memorize the training data. And you actually have an operational way of doing that, because if the difference between training set error and test set error is too large, you know that your network has too much expressive power. Chop off some hidden units. And if you cannot reduce the training set error enough, then you know you don't have enough expressive power. Increase it. Okay? So you look at the training set error and the test set error to make that decision. Ideally, you want to be able to find a solution for the training set to reduce the error to 0 or close to 0, but not easily. You want it to be difficult to do that. Maybe try it multiple times. If it's too easy, beware. Yeah?
Can we say eta is the selection of Roni data bias?
Is what? Is the learning rate a form of soft bias? Not the way I define soft bias, because the way I define soft bias has to do with the optimization criterion and not with the search. But it does affect what you end up finding, so it's a matter of definition. We didn't get to talk about how to represent categorical input, to rank categorical input, and all of that. Let me just leave you with one important observation or tip about the task, and I also posted it. A couple of people asked about, can I use a different transfer function here or there? Isn't that more suitable for this? Absolutely, yes. Yes, if you thought the task was about slavishly following my instructions, it's not. The task is about understanding what the problem is and making your own architectural decisions about what to use for what, based on everything you know and everything you learned. So you're allowed to use anything within neural networks, because there's a practice in neural networks. So not only you're allowed, you're expected to decide what to use based on everything you know. Thank you.